In this module, we'll be using systems theory to define the basic model of an ecological system. We'll firstly give a brief outline to the model of a system in the abstract, before going on to use this to interpret this thing we call an ecology. A system may be understood as a set of parts called elements and the relations between those parts through which the elements are interdependent in forming some overall macro-organization. Unlike a set of independent objects, the elements within a system are in some way interdependent. They all form part of some organization that they in some way contribute to and are dependent upon. Systems operate within some environment and have a boundary that defines the internal set of interdependent elements as distinct and in some way autonomous from their environment. Systems can be open or closed. Closed systems have a limited exchange of energy and resources with their environment. Open systems, in contrary, have a high exchange of energy and resources with their environment. They are typically non-linear and may be in a thermodynamic state of disequilibrium. A dissipative system is an open system that performs some function. They take in resources, perform some process upon them, and generate some output of energy and entropy. All biological creatures are open, dissipative systems. They have to import energy, process it, and export entropy. Systems have a hierarchical, multi-level structure, with smaller elements nested within subsystems that are, in turn, nested within larger systems and so on, until we get all the way up to the level of the whole environment. Nonlinear systems exhibit emergent properties, that is to say, components interact in a specific way to create a combined entity that is in some way more or different from the simple summation of its constituent elements. This is called a synergy, and this synergy results in the emergence of new patterns of organization as we go from the micro to the macro level. And thus, we get many heterogeneous, irreducible levels to the system that have their own internal properties, structure, and dynamics. Finally, systems are regulated by a set of negative and positive feedback loops that define the system's pattern of development over time. Dissipative systems require the maintenance of some set of environmental parameters in order to function. These environmental parameters are regulated through feedback loops, and the process whereby this takes place is called homeostasis. An ecosystem is then a physical system, composed of a set of biotic and abiotic elements. These elements are interdependent in affecting each other and the overall state of the system. An ecology is before anything else a physical system. That is to say, on its most fundamental level, we are dealing with the interaction of energy and matter. Energy is being processed through the system, and each stage of that process involves the construction and deconstruction of matter into various structures as the resources are processed across some potential energy gradient. Energy is being inputted to the system via the sun, geothermal energy or gravity, and these are driving some process within Earth's systems. That process takes place from some high potential energy source to some low potential energy sink. On an abiotic level, the ocean conveyor belt is driven by an energy gradient between the warm equator and the cold poles. The atmospheric winds are driven by an energy gradient between warm and cool geographical locations. On a global scale, the sunlight energy that reaches the Earth is eventually converted to low-level heat, leaving the Earth as radiation. On a biotic level, all biological creatures are driven by the energy gradient between the resources they consume and the entropy they export. Within biological creatures, we can call this process metabolism, as it takes place on every level, from the metabolic pathways in a single cell to that of an organism to whole networks of creatures that form part of macro-level metabolic networks processing energy and resources through the whole ecosystem. Here, we're referring to the word metabolism to refer to the capacity of a biological entity to harness and process free energy. All creatures have to intercept and process resources. In doing this, creatures serve the overall function of processing energy through the system along the food web. They form a network of nodes processing the system's inputs to its outputs. This process can be understood in terms of what are called sources and sinks. A general definition of the source-sink concept is based on net flows between components of a system. A source is a subsystem or element that is a net exporter of some resource, and a sink is a net importer of those resources. This flow of energy through the ecosystem is also referred to as the calorific flow. Through anabolic and catabolic processes, what is called the charge and discharge cycle, energy is processed through the network. Anabolism, which is the charge phase, is the incorporation of high-quality energy into biochemical structures, which keeps the system far from thermodynamic equilibrium. Catabolism is the discharge phase, corresponding to the deterioration of the structure with the release of accumulated chemical energy and its transformation into work and heat. The classical example of this charge and discharge cycle being the relationship between autotrophs and primary consumers, where the plants capture and fix energy into carbohydrates before this is discharged in consumption by the animals. In so doing, they complete an anabolic-catabolic cycle and transfer energy from high-potential photons across a gradient to low-potential dispersed heat energy. An example of a full energy flow would begin with the autotrophs that take energy from the sun. Herbivores then feed on the autotrophs and change the energy from the plants into energy that they can consume. Carnivores subsequently feed on the herbivores, and finally other carnivores prey on the carnivores. In each case, energy is passed on from one trophic level to the next trophic level, and each time some energy is lost as heat into the environment. This is due to the fact that each organism must use some energy that they receive from other organisms in order to survive. The flow of resources through the metabolic network defines what is called the energy pyramid. The efficiency with which energy or biomass is transferred from one trophic level to the next is called the ecological efficiency. The percentage of energy at one step of a food chain that is available for consumption by the next step is called the food chain efficiency. It is calculated as the energy in the food minus the energy used for respiration. It is approximately 10% to 50%. In this process of energy being transformed through the system from input to output, the system becomes an ecological network of components that have to fit together in some way, as they are interdependent in processing their inputted resources. From the different cells and organs in our body self-organizing around the collective function required to process resources through the system, to the self-organization of creatures within whole ecosystems as they co-adapt and co-evolve to perform differentiated niche roles with respect to each other. In every ecosystem, abiotic and biotic plants, animals, and microorganisms fit together functionally. Wherever it was thermodynamically feasible to transform matter, a biological system has been created to do that. This insight has been captured in the so-called maximum power principle, MPP, first posited by Alfred Lotka. which states that self-organizing systems, especially biological systems, capture and use available energy to develop network designs that maximize the energy fluxes through them, which are compatible with the constraints of the environment, and that those systems that maximize the throughput will endure. Thus, the maximum power principle governs expediencies or efficiencies in both the ecosystem's functional and structural development. Another way of understanding this is through the more general theory of what is called the constructural law. Constructural law is a term recently coined by Adrian Benjamin to describe the natural tendency of flow systems such as rivers, trees, lungs, tectonic plates to generate and evolve structures that increase flow access. It holds that shape and structure arise to facilitate flow. The designs that happen spontaneously in nature reflect this tendency. They allow entities to flow more easily, to measurably move more resources further and faster per unit of useful energy. Like all complex systems, ecosystems are multi-level or multi-tiered systems that form some kind of hierarchy through the process of emergence. Shorter, faster, biotic processes are nested within and dependent upon longer, slower abiotic processes, meaning that the biotic levels in the ecosystem are largely defined by their geographical conditions under which they have to operate. That is to say, the abiotic conditions largely define the outlining parameters to the biotic levels. This structure to ecosystems, where the set of abiotic parameters shapes and defines the biotic elements within the system, can be understood in terms of what is called the environmental gradient. An environmental gradient is a gradual change in abiotic factors through space and time. Environmental gradients can be related to factors such as altitude, temperature, depth, ocean proximity, or soil humidity. Species abundance usually change along environmental gradients in a more or less predictable fashion. However, the species abundance along an environmental gradient is not only determined by the abiotic factors, but also by changes in the biotic interactions. These parameters within which an organism or ecosystem can function may be understood as its boundary condition. All organisms and ecosystems have some kind of boundary condition. The system's boundary demarcates a limit to its internal components and processes. On a theoretical level, a boundary can be understood as a mechanism for regulating the inputs and outputs of energy and entropy, and through this, the maintenance of the system's integrity. Internal to its boundary, the system has some degree of integrity, meaning the parts are in some way operating cooperatively, working together, and this integrity gives the system a degree of autonomy. For example, if we take a tree, every part of the tree has been designed in some way to function as part of the entire system. The bark, leaves and trunk all serve some function with respect to the whole, and thus they are integrated, and through this integration they are able to function independently from other systems in their environment. Thus the leaves in the tree are dependent upon the tree's trunk and all the other elements to that tree, but they are independent from the leaves and trunks of other trees. That is to say, the tree as an entirety has some degree of autonomy. A system's boundary is then demarcated by where the nexus of relations that enable it to function as a semi-integrated and autonomous whole reach their limit. Beyond this, the system loses its autonomy and has to interact with other systems in its environment. In the real world, all living organisms have boundaries. They are protected by skins, cuticles, a shell, or at least a resistant membrane that delineates them. Within ecosystems, this boundary may be termed an ecotone, which is a transition area between two biomes where two communities meet and interact. An ecotone may appear on the ground as a gradual blending of two communities across a broad area, or it may manifest itself as a sharp boundary line, such as a cliff or seashore. Ecosystems are dynamic entities. They change over time due to various endogenous and exogenous factors, such as abiotic disturbances like earthquakes or floods. At the same time that they are continually changing, they also have to maintain some form of stability to certain critical parameters, such as the pH level to soil or temperature, which are required for enabling organisms to function. This process, whereby organisms or whole ecosystems regulate both change and continuity, is called homeostasis, and homeostasis can be identified as one of the defining features of life. The actual mechanism through which this is done is called feedback loops. On the micro level of an individual organism, these feedback loops may be controlled by a centralized regulatory system. But on the macro level of a whole ecology, this regulation process is distributed out across many different feedback loops between many different species and geological factors. The counterbalancing process of negative feedback works to stabilize the system into a steady state of development, while positive feedback can work to drive nonlinear exponential growth or decay, creating ecological disturbances such as hurricanes, climatic runaway effects, or population outbreaks. In this way, ecosystems can exhibit long-term stable development balanced by negative feedback as seen during the process of succession, but also they may go through periods of rapid nonlinear growth or decay such as ecological collapse. The long-term process of change within a biological population is understood through the theory of evolution. The theory of evolution is typically presented in an atomistic form as a narrative surrounding individualism, competition, and the survival of the fittest. But within systems ecology, this process is understood in terms of the thermodynamics of the system's metabolic networks, within what is called the maximum ecoexergy principle. Here, we're looking at evolution not so much in terms of the individual organisms, but more in terms of what it means for the whole system. As the scientist Alfred Lotka wrote, it is not so much the organism or the species that evolves, but the entire system, species and environment. The two are inseparable. As we've previously discussed, the elements of an ecosystem are organized as a network in which they fit together functionally. The community assembly process is able to select from a pool of species with the potential to fit together, because species that have lived together in the same ecosystem for thousands of years have co-adapted to each other through biological evolution. As the community assembly process forms a food web, it selects only species that fit into the existing web. If the ecosystem receives more free energy than required to maintain its function, the surplus free energy will be applied to move the system further away from thermodynamic equilibrium. Ecosystems offer many possibilities to move away from thermodynamic equilibrium, and they select the pathway that moves the ecosystem furthest from equilibrium. Those pathways are enacted through different species or gene pools. The maximum ecoexergy principle states that ecosystems will develop towards higher levels of ecoexergy, where ecoexergy simply means the current stock of available energy. In so doing, they will move further away from thermodynamic equilibrium. Evolution can then be understood as a process of selection over a set of ecological elements that will best facilitate this process. In this module, we've been taking a very high-level overview to ecologies through the lens of systems theory. We first discussed how an ecology is, before anything else, a physical system where we're dealing with the interaction between energy and matter. Energy is being processed through the system, and each stage of that process involves the construction and deconstruction of matter into various structures, what is called the charge-discharge cycle, as energy is processed across some gradient through a network of biotic and abiotic elements. We then went on to talk about the maximum power principle, a process of self-organization where given enough input of free energy, the system will endogenously self-organize to maximize the energy flux through the network as creatures co-evolve and co-adapt to occupy the various niches required. We talked about boundary conditions as a universal feature to biological systems, ecosystems dynamics and homeostasis as a process of feedback loops. Finally, we talked about evolution as a process of selection over a set of elements to maximize the throughput to the ecosystem's metabolic network.